right, hello, welcome to Light Calculations. Hopefully you are viewing this video after you have gone through and filled in the notes for the PowerPoint. So, because we need this information right up here. So if you have not done that already, I would recommend pausing this video, going back and filling out the notes, and then coming back. But if you already have that information, wonderful. We are going to just solve some problems. That way you can kind of get an idea of how it works if you still need a little extra help. So we do, like I said, need that information up there, but instead of me moving my paper up and down, I have written everything we need on this note card. So I'm just going to be referencing this as we solve. So the first thing we're going to do is obviously read our problem, right? The problem says if the wavelength of light is known to be 5.5 times 10 to the negative 7 meters, what is the frequency? So we are solving for frequency. So the thing that we need to do is look at all of our formulas and find which one has frequency and wavelength, what we've been given. If you do that, you'll notice that the only one that has both of them is this first one, so we're going to go ahead and write that one down. So we have speed of light equals wavelength times frequency. Now we're solving for frequency, so we're going to go ahead and get frequency by itself, and we do that by just dividing by wavelength on both sides. So we should end up with V equals C over lambda, or speed of light over wavelength. And if we remember, our constant, one of our constants is speed of light, is C, and that's 3.0 times 10 to the 8th meters per second. We've been given wavelength, so we have everything we need already. So all we have to do now is just plug it in. When we do that, we'll end up with C, which is speed of light, our constant, 3.0 times 10 to the 8th, sorry. And I almost always represent times 10 with an E. It means the same thing, that's just how I write it. So E, 8 meters per second, divided by our wavelength, which was given to us in the formula, in the question, sorry, 5.5 e to the negative 7 meters. And now we're solving for frequency. All we have to do is divide. So when we do that, we'll get 5.5 times 10 to the 14th. But what is my unit? Well, if you didn't know frequency, right? Frequency is 1 over S, S to the negative 1, hertz, all of those. Okay, so I'm going to use hertz. But you could also write 1 over S or S to the negative 1. And if you had no clue what it was, we can use our math that we did here to figure it out. So if we have M on top and M on bottom, well, what happens? They cancel each other out. So we are left with just 1 over S, which is what that is here, which can also be written as S to the negative 1, and both of those also mean hertz. Wonderful. Great job. Now let's move on to the second one. This one says if the frequency of light is known to be 9.45 times 10 to the 14th hertz, would the light be visible? If not, would you predict it to be UV or IR, ultraviolet or infrared? So the first thing we need to do is figure out what we're solving for. So at no point does it actually tell us what we're solving for, but I want you to go back and think of your notes and think of what we used to determine if it fell in the visible spectrum. Well, we used meters, right? We used the wavelength. So in order to determine if something is visible, that means that we have to solve for wavelength. So let's go ahead and do that. We've been given frequency. We need to solve for wavelength. Well, that's basically the same thing we did up here, just backwards. So our formula is still C lambda V. We'll rearrange it now to solve for wavelength, which would get us lambda equals C over V. Okay? Now we plug it in. We still have C. That is still 3.0 e to the 8th meters per second. And this time we've been given frequency, so we'll plug that in. Reminder, S minus 1 is the same thing as 1 over S. So those cancel out, right? And then our unit we're left with is meters, which is almost always what we're solving with for wavelength. But remember, wavelength can be in meters or nanometers. All right, so let's plug that into the calculator. And when we do that, we should get, let's see, divided by 9.45 to the 14th. So we should get 3.17 e negative 7 meters. All right, so now we're in meters, but how do we know if it's visible or not? Well, what was our range of visible light? Do we remember? It was 700 nanometers to 400 nanometers, okay? So if you remember, I went ahead and flipped back. So if you remember, our visible light spectrum is from 700 to 400 nanometers, okay? If you were absent and you were not able to get this, I would make sure that you get one from your teacher. It's going to be very helpful. So these are nanometers. However, we mentioned that this up here, it is all in meters, okay? So how do we reconcile nanometers and meters? Well, we convert, right? So 700 nanometers is the same thing as 7. I'm going to write times 10 for this one, and I'll show you why. To the negative 7 meters, okay? 400 nanometers is 4 times 10 to the negative 7 meters. They're the same thing, which means our visible light spectrum is going to be in the 10 to the negative 7 range. It's not all 10 to the negative 7, okay? But both of these are negative 7. So if you end up with a number, if you end up with your answer being 10 to the negative 7, check your first number. If it is between 4 and 7, then it is visible light. So let's go and look at our problem. Okay, so our problem, our answer was 3.17 times 10 to the negative 7th, right? But we just said that this goes from 7 to 4 times 10 to the negative 7. So does this fit inside this range? No, it doesn't. So that means it is not visible. And the next question asked is this higher or lower? It is a smaller number than 4, not a larger number than 7. So since it's smaller than 4, we need to look on the right side of our spectrum, which means we are left with ultraviolet. Great job. Wonderful. Let's flip to the next page. We got 4 more. So this first one, I'm going to scooch it out a little bit. This first one asks, what is the wavelength in meters of the electromagnetic carrier wave transmitted by a radio station at a frequency of 640 kilohertz? It's kind of a lot of words, so let's break it down. First thing is, what is it asking us to solve for? It's asking us to solve for wavelength in meters. What does it give us? It gives us frequency. Okay, so let's look at our formulas. Which one gives us wavelength and frequency? Well, that's our speed of light. So, you write that down. I'll give you a hint. Anytime you have to use this, we're going to have to rearrange it. Because guess what? Our speed of light, our c, is a constant. So we already know what that is. Let's rearrange it to solve for wavelength. We have c, we have v, but what's the problem here? Well, our problem is that we were given in kilohertz. But have we used kilohertz at all? Is that one of our units that we talked about? No, just hertz. But thinking back to our very first unit, what does that K stand for? It stands for kilo, right? Well, how can we deal with prefixes? We can use dimensional analysis to convert. Now, when converting a simple kilo, you're not going to have to show me dimensional analysis. Hopefully, we know that kilo is 1,000, right? So if you choose to just take this and multiply by 1,000, awesome. But I'm going to show you dimensional analysis. So we're starting with 640 kilohertz. How do we get to just regular hertz? Well, kilo goes on bottom, right? And regular hertz goes on top. If you choose to use the regular, just the scientific way, we would end up with one, we would end up with 1, and then 1e to the third, or just 1,000. I realize that kind of got small to see. I apologize. My parentheses were a lot closer than expected. So really what we should have here is just 1,000 hertz. It's the same thing, okay? So now we solve. Plug it in. I'm going to bring it back out. And when we do that, we should end up with 6.40 e to the 5th hertz. Now this number is what we can plug into our formula. So when we do that, as always, our constant is the same. Now we can plug in our frequency, this one, into here. To the 5th hertz. Okay? Now, let's go ahead and solve. So when we do that, we should get, go ahead and pause it, solve for yourself, but we should get 470 meters. And we get 470 as our final answer. Why? Sig figs. We have 2 sig figs here, and what we were given in the problem contained 2 sig figs. So 470 meters, or if you prefer scientific notation, 4.70 e to the second. All right, now we get to move on to energy. So now we're using a different formula. We have one formula for energy that we can rearrange and get a different one. So if we remember, V, right? V is up here. So many times have we rearranged our C equals wavelength times frequency to get frequency. Okay, and what does that look like? C over wavelength. Well, what is it here? C over wavelength. You may also see this written like that. They're the same thing. Okay? So, here we're looking for energy. So, energy equals, all we've been given is frequency. Well, then what formula are we going to use? We want to use our HV, right? Because what we have frequency and then H. What is that? Well, G. It's a constant. So it stays the same each time, and it's been given to you in your formula chart. So our constant for H is called Planck's constant, and is 6.63 times 10 to the negative 34 joule seconds. So let's plug everything in. We get 6.63 so that's my J. Don't be confused. That's just my J. Times frequency, which we were given here. Hertz. But remember, Hertz is also 1 over seconds. G, joules is joules times seconds. That's energy. Planck's constant is joules times second. Well, if we do second times 1 over second, we're left with just joules. So whenever we solve for energy, our energy unit is joules. When we solve, all we do is multiply, and we get 5.20 e to the negative 18 joules. Awesome. 2 more. Let's get through them. This one says if 1 photon of light is known to have the energy of 3.33 times 10 to the negative 19 joules, is the light visible? Reminder, when it asks, is the light visible, we are solving for wavelength. So looking at our formulas, what formula do we want to use that has energy and wavelength? Well, this one, right? So we're going to plug that in. All right. But we're solving for wavelength. How can we get wavelength by itself? Well, first thing we want to do is get rid of it on the bottom, right? It's not helpful if it's left on the bottom. Then it's 1 over wavelength that we're solving for, not just wavelength. So we'll multiply by wavelength on both sides. So then we get wavelength energy equals HC. To get wavelength by itself, divide by energy. So our final formula that we want to use is HC over energy. Well, H and C are constants. We were given energy, so now all we have to do is plug it in. If we remember, H is 6.63 e to the negative 34 joule seconds. C is speed of light. That's 3.0 e to the 8th meters per second. All over energy, which is 3.33 e to the negative 19 joules. Hopefully you followed me where we got. If not, go back and rewind, go step by step. So all we have to do now is solve, plug it into the calculator, go ahead and pause the video to solve it yourself. But the answer is 5.97 e to the negative 7 meters. So we solved for wavelength, but reminder, that's not answering the question because the question is asking, is it visible? So let's reference our spectrum, right? Visible light goes from 7 times 10 to the negative 7 to 4 times 10 to the negative 7 meters. Does this fall within this range? Yes, it does. So that means that our answer is yes, it is visible. Y'all are doing awesome. We have one more to work through, so let's get to it. If a light has a wavelength of 6.6 times 10 to the negative 7 meters, what is the energy of one photon of this light? We're asking for energy, right? So that means we have to use an energy formula. It gives us wavelength, which means we probably want to use this one. And G. Now all we have to do is solve. H, just like before, 6.63 times 10 to the negative 34 joule seconds times speed of light, 3.0 e to the 8 meters per second, divided by the wavelength which was given to us, 6.6 e to the negative 7 meters. Well, the meters cancels out, the 1 over seconds and the seconds cancels out, so we're left with just joules, which should be our unit. So when we plug it into the calculator, we're going to get 2.98 10 to the negative 19 joules. Great job. Thank you for hanging through with me for this 22-minute video on light calculations. If you still have questions, please go see your teacher. We are always happy to help you. Reference the tutorial schedule that is linked in Canvas as well as posted in all of our classrooms. Otherwise, I hope you have a great day, and thanks for hanging around.